So I want to talk to you about quadratic expressions. So first of all, I want to talk about the meaning of this adjective quadratic. And a quadratic expression is one that can be rewritten. Oh boy. One that can be rewritten in the form number times x squared, number times x, and number all added together. A and B and C can be whatever numbers you want. Any real numbers that you like. So you can be a nice number like 3 or 5 or -1, but it could just as easily be the square root of 2, 3/5, or even pi. They're just real numbers. There's only one restriction, and that's that the coefficient of x squared is not allowed to be 0. You have to be able to, in a sense, see an x squared there. And that's where the name of this comes from. Quadratic, quad, is referring to something that's square or rectangular, and that is trying to evoke this exponent here, this exponent of square. Now, I say quite carefully that the expression can be rewritten in this format. It's possible that the expression doesn't come to you in that format to begin with. So let's do some practice, trying to identify some quadratic expressions versus some not quadratic expressions. Let's take, for example, x squared plus 3. What do you think? Is this expression quadratic or not? And if it is, what would you say is the value of A, comparing with up here, the value of B, the value of C? Now at first, this one might seem like it's not quadratic, because the quadratic expression is supposed to have 3 terms, 3 things added together, but ours only has 2. But that's okay. We're going to rewrite this expression so that it looks a little bit more like this one. Now, I'm going to start with the x squared in the lead. At the moment, it doesn't look like it's being multiplied by any number at all. But there is a secret number, a special number, that when you multiply by that number, it becomes essentially invisible. And that's the number 1. 1 times x squared, the 1 vanishes and becomes just x squared. 1 times x squared in the lead. In the back, I have plus 3. And in the middle position, I'm going to indicate how many x's that I have. Not x squareds, but how many x's that I have. Well, my expression has 0 x's. My expression has no x's. And so I'm going to reformat this as 0 times x. 0 times x is the same thing as 0, which doesn't change this sum at all. So what I have written down now, in the more standardized format, is equal to, is a rewrite of what I started with. But having rewritten it, it's easier for me to say, first of all, yes, it's quadratic. And second of all, it's easier for me to see that A, the coefficient of x squared, is 1. B, the coefficient of x, well, I don't have any of those. And C for the constant term, the number of 1's, is 3. Okay, what about this expression? Now this one looks very strange because at the moment it seems like we don't have any x squareds. And if we don't have any x squareds, is the expression really quadratic? Well, let's again make an attempt to rewrite this expression. Let's try and rewrite that so it's at least closer to this other format. Now I have 1, 2, 3 things multiplied together. So I'm going to follow PEMDAS, and I'm going to take these products as I encounter them, moving from left to right. So first, I'm going to take the product of 2 times x minus 3. 2 times x minus 3 becomes the quantity 2x minus 2 times 3, or 2x minus 6. Now, having the first product done, I'm going to take the entire result of that and multiply that result by x plus 1 in the back. So I'm going to distribute. Sometimes folks will say FOIL, first, outer, inner, last, to say that 2x times x. All right, folks, try that one yourself. What's 2x times another x? 2 times x times x. X times x can be thought of as x squared, 2x squared. Now, looking at the outer product, 2x times positive 1, the result of that is positive 2x. The inner product, negative 6 times x. Not much you can do there. And finally, negative 6 times positive 1. Now, if I go through and combine like terms, and combine terms with the same exponents, I discover that I have 2x squareds, negative 4 x's, and negative 6 in the ones position. I would conclude that yes, this is quadratic, with a equals 2, b equals negative 4, c equals negative 6. All right, what about this one? 3x plus 1. Again, there are 2 terms, just like in part A. There are 2 terms, whereas usually we have 3 terms. Now, in part A, we sort of wiggled our way out of that problem by putting a term in that had a 0 attached to it, so that it didn't really count. So let me try and put an x squared in that has a 0 attached to it. Maybe the same trick will work. Now, based on that, I would say that a is 0, b is 3, and c is 1. But there's a problem here in the front. If a is 0, and I look back at the definition, I get a problem because for a quadratic expression, a is supposed to be non-zero. So this term, really, no matter how you rewrite or try and be tricky, this is not quadratic. I'll just put not for short. Not quadratic. Now here's a final exercise. This one here, negative 4, x minus 1 squared plus 5. I'm going to go through this one a little bit quickly. X minus 1 squared, I can rewrite as x minus 1 times x minus 1. Now let me again follow PEMDAS. Taking the first product I see, negative 4x, negative 4 minus 1. And then just as in the previous part, I'm going to FOIL, I'm going to distribute, and I'll get negative 4x squared, negative 4x, x. I get negative 4x, negative 1 times positive. In the center, 4 times x. On the outside, 4 times minus 1. And then this lingering plus 5 from the outside. And after combining negative 4x squared, 8x, and 1, I would conclude that yes, this is quadratic, with an a of negative 4, a b of 8, and a c of 1. So I just wanted to give one last comment here, one last one, to say that what is the meaning of this term standard form? Standard form is used to describe a quadratic expression that is written in the form ax squared plus bx plus c. So someone has already done the work, multiplied everything out, combined all the like terms, and they have given you something in this format. So this is just a way of describing what a quadratic expression looks like at this moment.